In this video, we're going to be solving a problem determining the number of monochlorinated products, also molecules. And the particular question asks which of these compounds will give 4 monochlorinated products excluding stereochemistry. So I'm going to draw the molecules first. And here you have, this is 1,3 dimethyl cyclohexane, and then I have another molecule which is the 1,4 constitutional isomer, so 1,4 dimethyl. And here the next one is the 1,2 constitutional isomer, so 1,2 dimethyl cyclohexane. Cyclohexane here. Okay, so first, how to determine the monochlorinated products. Remember that when you're doing halogenation, the useful reactions are when you're doing chlorination, and you can do that with chlorine and light or heat, and you can also do bromination, but typically bromine will give mostly one product, and it comes from the more substituted radical being the more stable. However, chlorination gives you multiple products. So here we're going to determine how many for each of these molecules. So first, notice that if I make a substitution, let's do it one by one, on one of the metals, that is, I replace one of the hydrogens in the metal by a chlorine, I have one of the products. Of course, this is going to be identical to the product that I get by removing one of the H's here. Now I have, this position is primary, will form a primary radical intermediate. Another product that I can form is actually by doing the substitution here. And I'm going to label this position B. So, and that is coming from a tertiary radical. So you will abstract the hydrogen here, form a tertiary radical, and that's your product. Then you will have another possible product will be, this is your initial molecule, but if you remove one of the H's here, and that is another monochlorinated product. And another that I can have is, so I'm going to see, and now I have this 2, 1, 3 positions. I can have a halide here. But notice that this position I am going to label D, and it's actually identical to that. And yet I have another possible product. So having the 2 metals, 1, 3. But now I have this product. Notice this is different from the previous. Notice here, this is 1 carbon away from the metal. This is right next to the metal. So this is product A. So now I see we have 5 different products without stereochemistry. What that means is here we're going to be checking if we're forming a chiral center in any of those. If this is the case, we need to remember that radicals have a trigonal planar structures. Therefore, if these 2 groups are different, the 3 groups, let's say, R1, R2, R3, when you add the halide, you're going to form a chiral center. And because the attack can be from either side of the plane, you're going to make in 2 enantiomers, so a racemic mix. So let's analyze this product. So one by one, this is not a chiral center. Remember that here you have 2 H's, so not chiral. This molecule here, the carbon is attached, so metal, chlorine, and if you travel this way, is identical to that way. So also not a chiral center. So only one product there. if I see this molecule, here we can do a plane. Let's say that the two metals here, I didn't specify stereochemistry. So this could be if the two were up, let's say like this conformation. And let's do that for the sake of this problem. I'm going to do this. Oh, I forgot one metal in this product, and that is an error, but it's okay. We're gonna, now I found out because I have forgotten that metal, I have found that the center is actually chiral. So here you will have this, and here you can have, drawing one of the possible, so say that you have this, and this plus the enantiomer. Again, when I didn't have that metal, it looked like two equal substituents traveling one way or the other, but the metal is there. So this is side, let's say this chain is different to that. So that is a chiral center, not a star. So these are two products, not one. This is only one. And here to keep the same nomenclature. So here, if you see this one now, this has a plane of symmetry right there. And so the that you're not creating what it means is this center has one substituent the same to the other. So traveling this direction and traveling that direction. So that's not a chiral center. Now analyzing the other product here. Let's do this. I could have that chlorine. I'm going to do a wiggle line, meaning that that could be on wedge on dash. So, and this is a chiral center because if I have a chlorine, I have an H, and now traveling in this direction is different from that direction. So we will have two here. And what they're not really, I'm going to erase that. The configuration of this center could be different, of course, but these two are not changed. And in this particular case, we have one chiral center here. Here, this is another chiral center, and yet this is another chiral center. When you have here, you have three chiral centers, and you can have an, say, one of the products have this chlorine on the wedge. Remember that you could attack from either side, but the other possible product, you will have, say, this on dash. And these two are not related as enantiomers. These two are diastereomers. And here, in this case, there's also not an enantiomer. Why would be that? Well, that is a chiral center, but now this is also a chiral center. And again, when you have the one of the center would be inverted, so you will have the two possible attack from the bottom and from the top, but this, the other center remains the same, so that will have the diastereomer. It's not an enantiomer. So to be an enantiomer, remember that if you have this, and say that I have a chlorine, that is a chiral center, and that is the enantiomer. But when you have another chiral center, if you don't invert it, then they're no longer related as enantiomers, but as diastereomers, like my example there. These are enantiomers. Again, here, one chiral center is inverted. The other two chiral centers are not. Here, at this molecule, let's keep our wedges here. So the problem's thing easier, but now you see that you have a number of stereoisomers that you can form. Constitutional isomers in between, say this and that, because the chlorine is in different places, but these two are stereoisomers. Now here in this molecule, chiral centers, we will have, say, let's do this on a wedge for now. But now this center, we have multiple chiral centers again. So chiral center here, This is also chiral because traveling, so metal, hydrogen not pictured traveling this way is different from this way. So chiral center, chiral center. And again, you will have that plus another product here. So when the problem says including a stereochemistry, so how many products including a stereochemistry, you need to do all this. But if it's not, then you can only just keep the substitution pattern. So like the one that I have there. So now let's do the 1/4. For the 1/4, I can have, let's make it faster, this and this is the same product. So you will have chlorine and chlorine, metal here. And again, you will need to find out whether you have chiral centers or not. And if you're given this, for example, as a particular configuration or not. But this is actually the same if you rotate it. It's a meso compound. Now, you can have now substitution. So A, you can have in B. That will be a tertiary. So here we'll have chlorine, chlorine. And again, check out stereochemistry as I did in the first. So here I'm not considering any stereochemistry of those centers. And so that's product B, doing the tertiary. And I can have the substitution here. But this is actually identical to that and identical to that. So without stereochemistry, I have 3 possible products for that. Now, in the case of the 1,2-dimethyl, I'm sorry. So I will have, say, this product without stereochemistry. All you have seen me doing all of the considerations that you need to do to get all of the possible stereoisomers. So product A, product here. Now you have another tertiary position here. That's another type of product. Not considering a stereochemistry, you can have this. Actually, that position is identical to that. And we will have a chlorine here. And now you can have another product. So we're going to label that D, and D, the final consideration is that. And we will do chlorine here and 2 metals. So again, depends, the number of products, final products, including a stereochemistry, will depend on whether you're given the configuration of the centers. Is this a chiral or not? Are you creating a chiral center? If so, the attack of the halide will come from either side. So pay attention to that to determine the number of monochlorinated products with a stereochemistry, without stereochemistry.